This video is on measuring energy changes. There are a lot of terms and units and kind of definitions in here, so make sure you pay close attention and make sure you refer back to this as needed while watching other videos or doing work in other parts of this unit. So first, we got to know what energy is. So energy is the capacity to do work or transfer heat. And work, you can see a couple down there, is the energy required to apply a force through a distance. So anytime you are applying a force and something is moving, you are doing work. So when you're doing work, you're using energy to do it, or transferring heat. So like heating the water on your stove, transferring it from your stove and the fuel in your stove, or the electric in your stove into the water. So units for energy are joules. There's the spelling. We use a capital J for that. This could be translated to kilojoules. And just like when you have like a kilometer and a meter, it's the same conversion, just a different base unit, just joules instead of meters. So a force is a push or a pull. Forces are measured in newtons. Work is also a joule. And the reason work is a joule is, physics students should know this, force and distance. So work equals force times distance. Force is measured in newtons, distance is measured in meters, and a joule is the same as a newton meter. They're the same thing. All right, so heat. Heat is energy transfer from a hot object to a cooler one. Heat will go in the direction of the cooler object or cooler surroundings. Also measured in joules. Then temperature. Temperature and heat are easily confused. Temperature is kind of that outward measurement of heat, like how hot or cold something is. Heat is how the temperature changes. So the actual scientific definition of temperature is the measure of the kinetic energy of the particles. So kinetic energy, remember, hopefully from 9th grade science, is energy of movement. So the higher the temperature, the more kinetic energy something has. The lower the temperature, the less kinetic energy, less movement. All right, so units for temperature are degrees Celsius or Kelvin. And if you remember from our gas laws unit, that if you want to go from degrees Celsius to Kelvin, you add 273. And if you want to go, if you want to go from Kelvin to Celsius, you would subtract 273. Because remember, Kelvin will always be higher because you can have negative Celsius, you cannot have negative Kelvin. All right, so we need to understand our system and our surroundings. And I referred to this a little bit in the specific heat video, but the system is what you're studying. So like if I have some reaction happening here, this is my system, but anything leaving that, coming or going, everything outside of that is what we call the surroundings. So there are two types of systems. You can have an open system. An open system is where matter and energy can be exchanged. So this would be like if you're adding heat to a pot of water on the stove, without a lid, that heat, that matter can leave, right? As you add energy to the water, it boils, and the boiling water, like the gaseous water, leaves. And energy leaves the pot. You can tell because if you touch the sides, it's warm. Closed, matter can't leave, but energy can, right? Your pot with a lid on it is still warm. You can still feel the energy change, but that gaseous water stays inside your pot. That's a closed system. All right. So all of this is a part of a bigger topic called thermodynamics. And the first law of thermodynamics is that energy cannot be created or destroyed. So all of the energy in our universe is already here. It just gets changed and rearranged into different forms, kind of like matter. So enthalpy is another word we use for heat. So this is very much like our Q, right? Q was heat. Enthalpy is also heat, but lots of times enthalpy will be measured in like a joules per mole situation. So we'll talk about that later, and you'll see that in a lot of tables with enthalpies in them. So this was talked about previously, endothermic and exothermic. So quick review, endothermic is when the system absorbs the heat from the surroundings. So endo meaning in, heat is thermic. So the heat goes in. So ice melting is heat going in. Boiling water is heat going in, right? You're putting heat into the ice, which is the system. You're putting heat into the water, which makes it boil. That's into the system. So anytime you go, if we talked about this, solid to liquid to gas, anytime you go in this direction, that's endothermic. You're adding heat. So your delta H, just like your Q, is positive. And it's written as a reactant. So if I had a reaction, not just a physical change like solid to liquid, if I had a reaction, I would actually write my heat on the reactant side. And you'll see we'll go over this in class. Exothermic, remember, then is released. So your system releases the heat. You're not putting it in, it's leaving the system. So combustion, right? Combustion, we actually talked about this. Like if you had methane, like CH4, plus O2 makes CO2 plus water. I don't know if you remember, we talked about how there's also energy as a product. We don't need it when we're balancing and stuff, but that is another product. So delta H is negative, just like Q, right? Q is also negative in this situation, and product, just like I wrote it here. And it could even be written as like a specific number, like this sometimes. All right, so this heat, this delta H, you will be able to look these up for specific reactions. That's where we're headed with this. So let's say we have this reaction in blue. A plus 2B yields C. And let's say I tell you the heat is negative 100 kilojoules. All right, so that we could look up. You're told that, no big deal. So then the question might be, the reaction in green, what is that one's delta H? What is that one's heat? Enthalpy. So look at the difference from the first equation to the second, from blue to green. It looks like everything is divided by 2. You see how 1A went to a half, 2B's went to 1B, and 1C went to a half a C. So from here to here, it looks like we're dividing by 2. So our delta H will do the same thing. So to go from here to here, we're going to divide by 2. Same sign, it would just be negative 50 kilojoules. So the second one we have here is delta H for a reaction is equal in magnitude but opposite sign for the reverse reaction. So look at this blue reaction again is still negative 100 kilojoules, same one as up above. But look at the second one in green. It's just reverse, so it's just flipped around. Your reactants are now your products are your reactants. So what happens here, oops, when it's reversed, is you reverse the sign. So it becomes positive 100 kilojoules. Now, is it possible you could have something that is halved or multiplied and reversed? Yes. All right. So we'll do some more practice with that in class. All right. So enthalpy diagrams. So we'll talk about like how to draw these diagrams that show how much heat is there and kind of if it's coming or going. So you can see we've got H, or our heat, on the y-axis, and the extent of reaction just kind of means like kind of like time, like starting to ending of our reaction. So reactants are turning into products. So if you look at both of these graphs, both of these diagrams, reactants are on the left, products are on the right, because reactants turn into products. The difference is, in this first one, reactants are above products, and the second one, it's flipped. So look what's happening here. Reactants are starting up above in our first reaction right here, okay? And they're ending with products down here. So delta H, just like delta T, is going to be your final minus your initial, okay? Which would be your products minus your reactants for your heat. Now look what happens. Products is lower than reactants. So you're going to get a negative value, right? Products is going to be less. When delta H is negative, just like when Q is negative, if I go back to here, this tells you that you have an exothermic reaction, because what's happening here is the temperature goes down as the heat leaves, right? Exothermic. So that makes it negative. So in the second one here, we've got reactants that start here for our heat and they end higher. So same thing, right? Your delta H is positive because now you're going to have your final, which is still your products, minus your initial, which is still your reactants, but now your product value is higher. So it's a bigger number minus a smaller, which gives you a positive delta H. The reason the energy goes up is because you're putting energy in, which gives you an endothermic reaction. Oops. All right, so the last little bit is when we look up enthalpy constants, you'll sometimes see them with this delta H and this little, they call it delta H naught. So these stand for standard enthalpy changes. So standard means we're under a certain set of conditions. And the conditions are as follows. They're a pressure of 100 kilopascals. That is sea level. That's 1 atmosphere, pretty close to what we're at right here in Minnesota. Concentration of 1 mole per decimeter cubed. Substances in their standard state. So what I mean by that is they're like in their normal state, like a solid, a liquid, or a gas. Like most, many things tend to be solids. And temperature is not technically part of the definition. However, you usually find it to be 298 Kelvin, which is, so it's about, it's 25 degrees Celsius, or about 76, 77 Fahrenheit. So it's around room temperature, essentially. So a lot of definitions, a lot of stuff in this video. We'll kind of pick this apart and apply it to a lot of other things going forward.